and let's see how much we can finish today. Okay, so we are discussing about what is solid mechanics, what is study using solid mechanics. So in the previous class we have detailed discussion about this, and in the introduction section we have seen for what the solid mechanics is used, right? Now while we study the mechanics of material or solid mechanics, okay, in that first thing you have to learn about stress, right? So what is stress? So if you see, the stress is a phenomena which is little different than pressure. So there is a confusion always comes in your mind that load divided by area. You define stress as load divided by area. But however, you see, whenever you define stress, you see stress is basically the internal resisting force divided by area. So when a body is subjected to external forces, then the body deforms, because that is what we study in solid mechanics. In engineering mechanics case, the bodies are rigid, so there is no deformation. However, if the body deforms, right, in that case, because of the deformation, the body always will try to resist that deformation, and for resisting that deformation, some resistive forces will be getting generated inside the body. So stress is nothing but the resisting force. So you can see, if I pull a bar, let's say, with force P, correct? And if I take any section, over here, then you will always see there will be a resistive force coming, which will be equal and opposite to the acting force, because the body must be in equilibrium. Because ऐसे नहीं होना चाहिए, it should not come like this, that body should break, right? If it breaks, then if body breaks, then it will not be actually under the elastic condition. Correct or not? Because until and unless till the time body does not break, or till the time the body does not yield, up to that point we are studying this. Right? So in that case, this reactive force will be equal to the active force, right? And if we divide this reactive force by the area, which is exactly equal to the force P divided by area, because of the equilibrium of the body, because body needs to be in equilibrium. That's why it is coming P by E. But ideally it is resisting force divided by E. Have you understood this? So now, if I take a bar like this, okay? So let's say it's a prismatic bar, okay? Prismatic bar means actually the cross-section area of the bar will be remaining what? Cross-section throughout the bar remaining fixed, right? Or same, right? However, you see, there may be cases where the dimension of the bar will be changing with the length. Okay. So now, if you see, if I take a bar something like this, correct, and if I act it upon with a force P, and if the area of cross section of the bar, the cross section may be a circular cross section, it may be a rectangular cross section, it may be a square cross section. Okay. And it is same throughout. Okay. So in that case, if the area is A, then if I take a section any point in the bar, so there will be resisting force coming, right? So if I take any section, if I cut it over here, then what I will get? I will get a resisting force something like this. So there will be a resistive force coming, which will be equal to R. So that R will be equal to P, and thus we will be defining stress. That will define as with the term sigma, and that sigma will be equal to P upon A. Or I can say, I should not say P upon A, I should say R upon A, where the R is nothing but equal to P. That's why I write P upon A. Is it clear? Now, if we go to the unit of the stress, then what will be this unit? The unit of the stress, you see, will be the unit of force divided by unit of area. So, if I go with the unit of force, it is Newton, and if it is area, then it is meter square. So, the unit of force will be Newton per meter square. So the area of the force will be Newton per meter square. Have you understood?
Yes, sir.
Okay, now considering this Newton per meter square, the confusion comes in your mind. I have seen in lot of cases, you could not go and understand what is Pascal. What is Pascal? What is Pascal? Pascal is the unit of pressure or stress. So how much is 1 Pascal? Is this Pascal? What is the megapascal? What is gigapascal? So see, these things you should remember. So not only this, so I leave it to you, because everyone should know what is Pascal, right? So you should know what is Pascal, what is megapascal, what is gigapascal, okay? And you see, megapascal, if you are studying your concrete technology and other subjects, then you see the compressive strength of concrete, characteristic compressive strength of concrete is given as 25 megapascal, right? So what does it mean? 25 megapascal means, what does it mean? The characteristic compressive strength 25 megapascal means the strength of the concrete is 25 Newton per millimeter square. So megapascal means 1 megapascal means 1 Newton per millimeter square. So I leave it to you. You please understand what is Pascal, what is megapascal, what is gigapascal. Because whenever you will be encountering the problems in your practical life, you will be getting the mixed mode of this kind of stress units. Because some cases you will see the units will be coming in gigapascal, some cases you will see the force will be given in Newton, some cases force will be given in kilonewton, and you will be asked to find out the stress in megapascal. So every unit conversion you should be conversant with. Okay? So in the next tutorial class I will be asking about all these things. Okay? What is the unit conversion and what is how do you convert everything? Okay? So now you see, if I find out the stress, where I have shown it over here, then you see this kind of stress, when a direct load is acting on the body, then this kind of stress is called direct stress. And when it is tension means it is a pull, right? Tension means it is a pull. So if there is a tension, a pull is coming into the body, in that case what will happen? We will call it as direct tensile stress. The stress will be called as what? Direct. So it is a direct stress. It is direct. Then we are putting tension. So tensile, and it is stress. So it is direct tensile stress. Correct? Now if we see, if instead of tension, if a body is under compression, so if I compress a body, then what will happen? So, like this, if I am pulling a body like this is actually tension, correct? Now, instead of this, if I force a body on this kind of force, where in both ways I am pressing this, right? So, it will be what? It will be compression. So, just in this opposite reverse direction, if we put a force, and in the direct nature of the force, then what will happen? Just like this, when I put a body and if I cut a section over here, then just in the reverse direction you will find the reactional forces coming, right? So it is not getting changed, right? It is not getting changed. So in case of tension, you see, when there is a pull, this way these forces are coming. If I am putting it under compression, you will see on this part of the body, this way the forces will come. So what will be the compressive or direct compressive stress then? Direct tensile stress is sigma is equal to P by A. So you see, direct compressive stress will be also equal to sigma is equal to R by A is equal to P by A, only with a change of sign, because it is happening in the opposite direction. Correct? So to differentiate between a tensile stress and compressive stress, we can take tensile stress as positive and compressive stress as negative. So I'll put a negative sign over here. Okay? Is it clear? So this is what is exactly about stress and tensile stress and compressive stress. Now if I go to this thing, I have told you what is the unit of Newton per meter square. Now what is Pascal, megapascal, gigapascal, I asked you. Okay, so you try to find it out. You have a proper unit conversion methodology in your mind, and you have to apply your mind over there, because not always all the forces, all the stresses, all the forces will be coming in Newton and meter. Okay, or Newton per meter square. You will be given with different kinds of units, so you should be very well conversant with these unit conversions. Is it clear? Now you see this. What does this mean? What does this mean? Sigma T del P by del A. So you see, in either of the tensile stress or compressive stress cases, if I take it, the resistive force is assumed to be distributed uniformly over the surface. So when I take this, what is happening? I am putting a compression, so the resisting force is coming in this direction, and resisting force is uniformly getting distributed over the cross section, isn't it? Uniformly getting distributed over the cross section. However, you see, if it does not the case, if it is not the case, that means if the resistive force is not uniformly distributed over the cross section, correct? Not uniformly distributed over the cross section. So let's say you have a uneven kind of body. Okay? You have body something like, let's say you have body something like this. And if you are putting a force P on this direction, and if you take a section over here, somewhere here, at this position, correct? So in that case, it may happen that the resistive force will not be exactly distributed in a what is called uniform pattern. Rather, there may be non-uniform pattern. And in such kind of cases, if you want to find out the stress, then what you have to do? You have to consider a very small amount of area, and you have to consider a very small amount of resistive force, that is delta P. So you see, if the force is not uniformly distributed, or the resistive force is not uniformly distributed, in that case, the intensity of stress at a particular point, if I want to find out stress, very important concept, okay? If a particular point, if I want to find out stress, then the surface is taken equal to the limiting ratio of del P by del A. What is del P? Del P means very small amount of force, or very small amount of resistive force. So this del P by del A, and when this del A, this small area, is tending to zero, that is infinitely small area, that is actually a point, right? So at a point, if I want to define stress, then I can define stress with sigma is equal to limit delta A tends to 0 del P by del A. Have you got it? So when the uniform distribution is happening for the resisting force, then I can directly write P by A. But if the uniform distribution of the resistive force is not happening because of the acting force, then I have to go with the limiting formula, and I have to take the differential to find out the stress at a particular point. Is it clear? Okay. Now with this understanding, let's now move to the next part. So whenever there is a resisting, whenever there is a force acting on a body, and in case of solid mechanics, as we are studying the mechanics of deformable bodies, so the body is deforming. So obviously because of the deformation, there will be something happening in the body, right? So deformation, because of the deformation produced by the force, there is another one concept comes that is called strain. So whenever there is a deformation, and what is strain? Strain is nothing but the deformation per unit length. Correct? Deformation per unit length. So if I say, if there is a bar, same bar if I take for example, and if I act it upon with the force P, and you see if there is a length increase of delta L, so if because of this force, if there is an increase of length by delta L amount, so if there is an increase of length by delta L amount, very small length increase, right? So because of that, if I want to find out this deformation in terms of strain, then how do I define strain? So because of this force, I will take it as tension. So tensile strain, I can say this is the deformation delta L by original length L. This is what is strain. Is it clear? So strain is defined as, tensile strain is defined as delta L by L. And what will be the unit? Because no unit, it will be happy, because both denominator and the numerator are having same unit. So strain doesn't have any unit. Correct? So now if the tensile strain is this, exactly the same way when I put a bar under compression, then what happens? So direct tensile strain, if it is delta L by L, if I put under compression, then direct compressive strain will be also delta L by L. However, I will define the strain with a negative sign. Clear? Yes. So with the concept of strain and understanding about strain, let us now move to definitions, few more definitions about solid mechanics. Very important things, that is, first thing is elasticity. Because you need to understand, because whenever there is a body deforms, that means that body is called elastic. Right? So what is an elastic body? What is an elastic body? So that definition you need to be very clear about. So what is elasticity? So you see, the elasticity is nothing but the property of the material through which, you see, if I load that material and if it deforms, after the removal of the load, the material should come back to its original shape. Correct? So no deformation should exist in that material. So no deformation should exist in that material. Is it clear? So if no deformation is existing, right, then we call it as elastic body. So what is elasticity? So that property of the material, so you see the definition, a material is said to be perfectly elastic. Right? So deformation is related to what? Deformation is related to strain. Right? So material is said to be perfectly elastic if the strain due to the loading disappears with the removal of the load. That means deformation disappears with the removal of the load. And the path to be followed for this coming back of this deformation to its original shape, that should be same as it happened during the loading process. So that's why we have shown it over here. So if I plot strain along x-axis and stress along y-axis, please remember this. This is very important thing. Okay, strain is always plotted along x-axis and stress is plotted along y-axis. Many cases I have seen you do it in the reverse, but it is not done in the reverse. So load will be plotted in y-axis and deformation will be always plotted in y-axis. So thus load divided by area, if I take, the stress will be plotted along y-axis and the strain, that is the deformation divided by the original length, will be plotted along the x-axis. Okay? So what I will say, this perfectly elastic material, when I say, then if I load, then the material will get strained. It will take this path. So this is an arrow, you can see. So it is strained and it is going to this. And if I remove the load from there, so load removal means I am removing the stress. So if I remove the load, the path followed by that will be the same as this one. So this is what is the characteristics of a perfectly elastic material. Have you understood? Now you see what is Hooke's law. So every one of you know Hooke's law, right? You have studied it in physics. So what is Hooke's law? So elastic material, it is applied in case of elastic material, and more precisely if you see, it is applied more precisely in case of perfectly elastic material. If a material is perfectly elastic, then you can apply Hooke's law. Okay? So what is Hooke's law? Hooke's law says stress is proportional to strain or strain is proportional to stress. Both way it is valid, vice versa. Okay? However, the definition is very important here. This term, within elastic limit. The material should be within the limit of the elasticity. Means material should not enter beyond the range of elasticity, or more precisely the limit of proportionality. That means limit of proportionality, we will see what is limit of proportionality, but for time being you understand the material should be under the elastic range to define Hooke's law. So what does Hooke's law say in that way? So Hooke's law says stress is proportional to strain, right? So Hooke's law says stress sigma will be proportional to strain epsilon. Whether it is tensile strain, whether it is compressive strain, doesn't matter. Okay? Strain is proportional to strain or vice versa. Strain is proportional to, it will be stress. Sorry. Yes, I will correct it. So strain will be proportional to stress or vice versa. Stress is proportional to strain. Correct. Absolutely correct. Typing mistake. So now you see the law is assumed to be applicable with sufficient accuracy to a number of engineering materials. Okay? So lot of engineering materials which we use in case of civil engineering, this law can be used perfectly. Hooke's law. Okay? And now if we see the difference between elastic body and rigid body, this is very important. Okay? Rigid body and elastic body. So you see, the rigid body when you see, so rigid body case, there are different cases of rigid body you have learned in engineering mechanics. So rigid body under motion. Okay? So the dynamics case you have studied, rigid body under motion. Okay? Kinematics you have learned, right? So when the rigid body under motion, there is no question of equilibrium. Okay? So when there is no question of equilibrium, then for the rigid body under motion, there cannot be any free body diagram. Because free body diagram only comes in case of the equilibrium condition. Okay, FBD, free body diagram. Everyone knows what is free body diagram? Engineering mechanics you have studied. Now you see, under equilibrium condition, rigid body can be also under equilibrium condition. When a rigid body is at rest, right? When it is at rest, at that time, you see, definitely there will be stress. So if you draw a free body diagram of a rigid body at rest, okay, let's say that bar example we have taken, let's say if it is rigid, then if I do it with a pool P, then obviously stress will be getting generated. However, we are saying that no deformation will be happening because the body is rigid. What does it mean? What does it mean? It means, you see, definitely there will be stress. Obviously there will be stress at that cut section. If I cut a section, there will be stress, right? However, strain is basically happening to be zero. Strain mania, right? And if you see, stress by strain ratio is what? Modulus of elasticity. Correct? Stress by strain is what? Modulus of elasticity. So now you see, if the body is perfectly rigid, then its modulus of elasticity will be infinite. It is not that stress is not getting generated. However, when you are thinking a body is a perfectly rigid body, in that case, the assumption is the modulus of elasticity is infinite. And that is why no deformation is happening. So it is not that in a rigid body stress is not getting generated. but the property of the elastic material that is coming into picture, that modulus of elasticity, it becomes infinite. Very good example, okay? Very good example. This is, you should understand what is difference between a rigid body and elastic body, okay? And then what is elastic body? So if you see, elastic body also can be under motion. It can be also under motion. So under motion, if there is an elastic body or perfectly elastic body, so what will happen? Not in equilibrium. It cannot be in equilibrium. Same case in the case of rigid body. As happens to the rigid body, same will happen to the elastic body also. However, you see, under equilibrium for elastic body or a perfectly elastic body, what will happen? The stress at a cut section and strain will be there, and note, perfectly elastic case, modulus of elasticity is constant. That means what? Stress will be proportional to strain, and the limit of proportionality in this case will be termed as modulus of elasticity, which is nothing but E. And what kind of stress we are talking about here? This sigma and this epsilon. What kind of stress we are talking about here? We are still now talking about the stress like direct tensile stress or direct compressive stress. Right? So stress is proportional to strain, and that can be equated with a constant, multiplying with the constant, that is modulus of elasticity. And if I take sigma by epsilon, will be always remaining constant, that is E, for a perfectly elastic material. Is it clear? Now from this, if I come to the definition of stress, and if I try to derive one expression for the strain, or if I want to find out what is the amount of elongation in terms of stress or load, then how do I find it? So it's very simple, you see. How do I define stress? I define strain epsilon as delta L by L, and I define sigma epsilon as sigma by E, isn't it? Sigma by E. So now, if I want to find out delta L, what is the amount of elongation because of a force P? So what is force P? So if I say now, I can write epsilon is equal to, what is this sigma? Sigma is nothing but P by A. So I can write epsilon is nothing but P by A. Correct? So if I write P by AE, and if I place this P by AE over here, so P by AE upon here, then what will be my delta L? So delta L will be equal to PL by AE. So the deformation due to direct stress and direct tensile stress or compressive stress will be equal to how much? PL upon A. Have you understood? How to find out the deformation in a body? This is very important. Now you see, if there are multiple materials joined together, okay, and because of the load, each and every material will be having separate deformations, and those deformations can be added together to find out the total deformation. And this adding up together of the deformations because of a load, or the deformations because of different loads in a simple material, when I am adding it up within the limit of elasticity, that is called principle of superposition. There are slides related to it, principle of superpositions. You will be able to understand in more detail about it later on. But principle of superposition says nothing but when I add it up because of different loads, there is a material is deforming. Let's say I am putting a load P1 on it, and there is a deformation delta 1, and then I am putting another one load P2 on it. So load is P1 plus P2, deformation is delta L1 plus delta L2. So this delta L1 and delta L2, if I sum it up, then I will get the total deformation under the load P1 and P2. And when it will happen? within the elastic limit of the material. So now you see this equation is very important. This equation is very important to remember, because you see delta L is equal to PL by A. Now you see I can write delta L in terms of stress also. So what will be there? So P by A is what? Sigma. So I can write sigma L by A. I can write sigma L. Sorry, sigma L by E. Correct? So sigma L by E. So these kind of equations you will be encountering a lot in the later stage of your study. Okay? So now if I go to a concept, I have put it at the last slide, I think. So let me go back and I'll come back to this. Let's say if I try to understand this concept of strain, okay? So strain is nothing but PL by A. Strain is nothing but PL by A. Now you must have heard about a term called strain energy. What is energy? Energy is nothing but work done, right? So basically, because of the strain, the amount of work done. So let us say if I apply a tensile or compressive force in a prismatic bar of cross section A and length L, so delta L will be the elongation, and delta L can be expressed in terms of PL by A. Correct? Now you see, when a tensile or compressive load P is applied to a bar, there is a change in length for an elastic material within the proportional, which is proportional to the load. So what is strain energy? Strain energy, this is a very, very important term, okay? So we are now understanding strain energy for direct deformation or direct deformation by tensile or compressive forces. This strain energy will be coming for all other different kinds of forces, and in your structural mechanics course it will be used again and again for solution of different kinds of problems. So try to understand this concept of strain energy clearly. Very important concept, okay? So what is strain energy? Very simple, however very important. So now we are understanding strain energy because of direct tension or direct compression. Now there may be strain energy due to shear, there may be strain energy due to bending, there may be strain energy stored in the body due to torsion. Okay? So for each and every cases there will be strain energy coming into the body. Whenever there will be deformation to the body. Okay? So now what is strain energy? So now strain energy of the bar is defined as the work done by the load. So work done by the load. And it can be very simply obtained. It can be very simply obtained. You see, within the elastic limit, if I draw a load deformation curve or a stress strain curve, okay, it will be a straight line. Isn't it? It will be a straight line. So you see, if I draw load versus extension curve, load versus deformation curve. So this is my load, and because of this, extension delta L. So there will be a straight line coming. So now, how much will be the work done because of this load P? Because the deformation is delta, so work done can be found out by the area under this triangle, isn't it? Yes. Work done is nothing but the area under this triangle, right? So what is work done? Work done is nothing but load multiplied by the deformation. But here we try to understand the area under the triangle. Why it is coming area under the triangle? Ideally it should have been, strain energy should have been P into delta. It should have been P into delta. But here you see, the value is coming, if I take the area of the triangle, it is coming half into P into delta. Why it is coming half into P into delta? It is not P into delta. Have you seen it? Because of the problem, because of the case, when we are talking about application of P is being gradually applied. You see, P is not suddenly applied. From 0 to P, it is reaching 0 to P. Because I cannot just pull, I am not just pulling it, I am gradually applying the load P. Okay, so when there is a gradual application of the load, which is the general case of our structural engineering also, in that case, your load is increasing from 0 to P. So the average load will be 0 plus P by 2. So it will be half. So half P into delta. However, on the other hand, you can directly get it from this load extension curve, and you can just take the area of this triangle, and that will give you the strain energy. So the strain energy value will be equal to U is equal to half into P into delta. Is it clear? Have you understood it? Now you see, if I take half into P into delta L, and I have told you that why these things are important. Okay? So P by A is nothing but sigma. So you see, P by A is nothing but sigma. So delta L can be written as sigma L by E. You have seen that? On the board I have worked out how delta L is sigma L by E. So if I put and P is equal to sigma A, what is P? Sigma is equal to P by A. Sigma is equal to P by A. So P is how much? P is equal to sigma into A. So now instead of this P, I am trying to define now strain energy. Instead of load and length increase, I want to define it in terms of stress. Okay, instead of load, I want to define it in terms of stress. So if I want to define it in terms of stress, then I am replacing this P with sigma A. I am replacing this P with sigma A, right? And also I am replacing the delta L in terms of stress. So delta L is in terms of stress is what? Sigma L by E. So I am replacing it sigma L by E. So how much it will come? Half of sigma square, and then half of sigma square E, half of sigma square by E multiplied by this A into L. Have you seen it? Is it clear? So this is also another one expression of strain energy, very important expression, okay? And you will typically observe the strain energy for shear, strain energy for bending, strain energy for torsion. Every cases, this expression will have a similarity. Because when there will be strain energy for shear, all of you must be knowing because of shear, what is the modulus comes? Shear modulus, G, capital G, right? So in that case, what will happen? U is equal to half of tau square by E, tau square by G. In case of shear, stress is how much? Tau. So shear stress, if it is tau, then it will become U is equal to half of tau square by E के जगह में क्या हो जाएगा? G. Okay? Bending stress, same thing will come. Torsional stress, same thing will come. Only the difference will be happening. The stress का जो ऊपर में जो definition है, that will change, and the modulus of proportionality, this proportionality modulus will change. In case of direct tension, direct compression, it will be E. In case of shear, it will be G. In case of torsion, it will be J, capital J. Okay? So there are different types of modulus we will be learning now. Okay? And we will try to understand this strain energy in different terms. But this strain energy understanding, concept of understanding strain energy is very important. Have you understood what is strain energy? Any question you have regarding the strain energy understanding? Any question? So strain energy is what? Strain energy is nothing but work done by the load to deform the body. That's all. Okay? And you calculate, and you see now here we are coming to a typical definition. This is very important definition. Okay? Many of you are not clear on this concept. Okay? So there is a definition called resilience. Resilience of the material. Okay? Resilience. How much the material is resilient to something. Okay? So this resiliency definition comes from strain energy. And it is very simple. You see? In that strain energy term, you see there is a term multiplied that is called A into L. What is A into L? A into L is the volume. Because anyway, if I take the area cross section A and length L, then A into L will be the volume of the body. Okay? So A into L is the volume of the body. So if I try to define strain energy per unit volume of the body, this is what? This is the total strain energy in the total volume of the body. Now, if I want to find out strain energy per unit volume of the body, so how much is the volume of the body? A. So per unit volume of the body, I will define it, divide it by A. So A will cancel. So the per unit volume strain energy is defined as resilience. Have you understood? So resilience is nothing but strain energy per unit volume. And what is strain energy per unit volume? Strain energy per unit volume will be having only this term, half of sigma square by E. Is it clear? Have you understood? So this is called resilience of the body. What is the time? 10:41. Lot of time. So now you see, you have understood this concept. You have understood this concept, resilience and all. Now again I go back and I take you through the more concepts or more definitions. So now you see, we have understood about, so we are here, right? So we are here. We are here, so up to this you are clear? From this we have developed deformation equation, what is the amount of deformation, and then we have defined what is strain energy for direct stress, and we have also found out what is resilience, right? Now let us try to move little forward and see what are the other things you need to understand. So you see, this is a very important concept. I think Anita Pan madam has already taken a class of you. And there she has discussed about what is a beam and what is the support condition, what are the support conditions, right? And how to find out the reactions in support. Okay, I'll also discuss a little bit later. Now you see, equilibrium of a body. You have already learnt it in engineering mechanics. Equilibrium of a body means when a body is subjected to different kinds of forces and moments, right? Where moments are also considered as force, right? So in that case, for a three-dimensional equilibrium case, summation of all the forces in x direction, y direction and z direction should be equal to 0, and summation of the moments about the x-axis, y-axis and z-axis should be equal to 0. This is what is three-dimensional stress case. On the other hand, if we take a two-dimensional structural case, then what will happen? The summation of forces in x direction should be equal to 0. Summation of forces in y direction should be equal to 0, and summation of the moments about z axis or the neutral axis, the axis which is other than the x and y, that should be equal to 0. Okay, so this is what is the condition of equilibrium. Okay, and on this condition of equilibrium, when you can solve or when you can find out the reactions in a body as well as the internal forces in a body, okay, using these equilibrium conditions, if you can find out the internal reaction forces, that means suppose I have this and if I am pulling it, this is the determinant body, right? And if it is a determinant body, then if I cut it, I can find out what is the reaction force inside, correct? And I do not require any other equation than these equilibrium equations, right? So when you can solve a structure, solving or solving a body means you are finding out the reaction components as well as the internal force components inside the body. So if you can find out the reactions and internal forces inside a body using the equilibrium conditions, that body will be termed as a determinate body. Okay, and that is what is called determinacy. Okay, and if you cannot solve a body under equilibrium using the conditions of equilibrium, then the body will be termed as indeterminate body. Okay, you will require some more equations to solve it. Okay, and you will learn it to solve indeterminate bodies in case of when you will be studying about structural analysis. Okay, now you see, if you move forward, then you see few more definitions. I have shown it over here. I have given you this example also, that I am loading it with P1, getting one delta 1 deformation. After that, I am increasing the load from P1 to P2, right? And my deformation due to P2 is getting increased from delta 1 to another delta. So because of this P1 plus P2, the total deformation is happening delta 1 plus delta. Okay? So if I find out the delta 1 because of P1 and delta 1 because of delta 2 because of P2, and I sum it up, I get the total deformation because of P1 plus P2. This is what is called principle of superposition. Have you understood? So for individual load cases, if I find out the deformations and if I sum it up, then I get the total deformation because of the total amount of load applied inside the body. However, within the elastic limit. Is it clear? So this is what is called the principle of superposition, and in this case also, if it is within the limit of elasticity, or if it is within the proportionality limit, then what will happen? If I remove gradually this load P2 and load P1, then gradually this delta 2 will vanish, and then again this delta 1 will vanish, and system will come back to its position, same as delta length L1 or L. Is it clear? So now you see principle of superposition. I have tried to show over here. Okay? So this is what is actually principle of superposition. You see what I have tried. So if I am subjecting a beam, this is a beam. Okay? It's a simple supported beam. On this side, this is a pin support. On this side, this is a roller support, right? And I am subjecting this beam to a point load as well as some varying load, right? And because of this beam will deform, right? So there will be a deformation pattern. And this deformation, if this direction is y, deformation will be a function of x. That means here the deformation will be different. Here deformation will be different. So it can be expressed as a function of x. So yx can be given as y1x plus y2x. What does it mean? y1x plus y2x means, if I now this determinate structure, if I take it individually separately, correct? So if I take individually separately, that means I take this structure only subject to this load, and because of that I get a deformation y1x, and because of only this, if I get y2x, then the summation of this y1x plus y2x should be equal to yx. This is what is exactly what you are saying in case of the bar extension also. Have you understood? So this is what is called principle of superposition. बहुत लोगों को ये समझ में नहीं आता है और बोल नहीं पाता है इंटरव्यू के टाइम. There's a problem. But you see, principle of superposition is so simple to understand. Nothing else. This is what is principle of superposition. Have you got it? Now with this, I think. So principle of superpositions I have explained over with this thing little bit words and all. So two requirements. You need two requirements. There are two requirements for principle of superposition you can apply. Okay. So two requirements. First requirement is material must behave in a linear elastic pattern. This is very important. So you need to follow Hooke's law for getting this principle of superposition. Okay. And the second one is geometry of the structure must not undergo significant change when the loads are applied. Small displacement theory. Basically, you cannot have excessive deformation of the structure. If excessive deformation of the structure will not remain inside the elastic limit, and you cannot apply principle of superposition in such cases. Okay? So have you understood? So let's stop over here today. Or please. So with this understanding, we will move forward in the next class.